Hi, we are 3C Engineering. This is our Capstone Design Project presentation for SDSU Spring of 2018. Let's meet the team.
Hi, my name is Nathan Bennett, and I was the project manager for this, and I worked on the site development.
Hi, my name is Sadar Ravi. I'm the geotechnical engineer, and I did the geotechnical analysis of this project.
I'm Lindsay Contreras. I was the transportation engineer, and I did the sewer study.
Hello everyone, I'm Ivan and I'm the transportation engineer for this project as well. I was also AutoCAD lead and GIS lead.
I'm Michael Ortiz, the construction engineer, and I worked on the water study.
Hello, my name is Jose Pimentel. I'm the hydraulic engineer and I work on the hydrology report and the stormwater quality management plan. Hello everyone, I'm Jesus Rodriguez. I'm the structure engineer and I worked on the structural recommendations for the building shell.
The project consisted of Sharp Healthcare Medical Office Building, consisting of a 86,500 square foot three-story building to accommodate on-site parking. To begin our project, we took a look at the topography map that was provided to us. Analyzing the existing surfaces, grades, and elevations, and possible obstructions, we needed to take a closer look at this to see the site for ourselves. Our first reaction to the site was that it was much bigger than we thought. Seeing the site also provided a better understanding for the contours being displayed on the topo base. In addition, we noticed an existing swale that runs between our site and the 52 off-ramp. This will later be helpful in stormwater management. The RFP called for the following in its scope of work: the site development plans, traffic analysis, stormwater analysis, water and sewer studies, a geotechnical study, and a structural analysis. There were three major considerations when planning the development for our project. Number one, to the south of our site, we were constricted by Caltrans right-of-way due to the butting up against the 52 off-ramp. Number two, to the north and east, there are residential homes. Finally, number three, to the west in the center of Quemac Street, there is a trolley system. The site development portion of the project is broken down into four sections: site layout, rough grading, improvements, and precise grading. This is the site layout for the project. Here is the rough grading plans, which show the proposed layout for the storm drain as well as initial grading. The improvement plans show the location of the proposed sewer and water lines. Finally, the precise grading plans show the final surface elevations along with the small storm drains lines used for landscape purposes.
In this portion of the presentation, I'll be talking about the traffic impact analysis that the new Sharp Medical Office Building will bring to the new site in Santee. Some of the things we'll be discussing is the new trips associated with the new proposed medical office building, potential traffic impacts associated with the new trips, and freeway analysis. In order to conduct the traffic impact analysis for the new Sharp Medical Office Building, the following references were used in order to analyze existing conditions. The first one was the Highway Capacity Manual, years 2000 and 2010, Santee's Mobility Element Report, Santee's Transportation Master Plan, and the SANTEC and ITE Regionally Accepted Traffic Impact Analysis Guidelines. Santee's reports were obtained from their website. The following intersections were used in the traffic impact analysis in order to analyze the existing conditions and the future impacts that the new Sharp Medical Office building would bring. 7 total signalized intersections were used in this study. One of the intersections was a two-way stop control. A total of 9 roadway segments were also analyzed in this traffic study report, with 7 roadway segments being on Cuyamaca Street and 2 roadway segments being on Mission Gorge Road, east and westbound. Here's a quick graphic of the project study area for the traffic impact analysis report. All 7 intersections were within city limit. 2 of the 7 intersections were Caltrans traffic signals. Another thing to point out was the MTS green light ran in the middle of Cuyamaca Street on the median. The following graphic shows the existing lane geometry at intersections for the project study area. Existing turn volumes and average daily traffic volumes were obtained from Santee's traffic engineer. Freeway and ramp volumes were obtained from Caltrans. In order to analyze the new traffic that the new site would bring, a trip generation analysis was conducted. In order to conduct the trip generation rate, we used the ITE Regional Accepted Code. In order to conduct the trip generation rate for this medical office building, ITE code 720 was used. There is an approximate 3,107 new trips that would be generated with this new Sharp Medical Office building. The following scenarios were also run on the traffic impact analysis report. Cumulative project volumes, existing plus project volumes, existing plus cumulative project volumes, and existing plus project plus cumulative project volumes. With the traffic impact conducted, we realized there was no necessary modifications necessary at the intersections. A new lane was added on the entrance of Cuyamaca Street with appropriate signing and striping.
The purpose of the hydrology report is to mitigate the increase in peak flow rates due to the site development. The first step was to delineate basins using the topo map that was provided. Existing and proposed peak flows were calculated using the rational method, Q equals EIA. Q being the flow rate, C the runoff coefficient, and I is equal to intensity in inches per hour, while A is the area in acres of the basins. To account for the increase in peak flows, a culvert of 2 inches in diameter was proposed, along with the addition of previous areas such as landscape. This picture represents the topo being divided into 3 basins, showing the Q, 100, the I in inches per hour, and the area in acres of each one. This exhibit illustrates the proposed conditions for the 3 basins, showing the Q, 100, the I in inches per hour, and the area in acres of each one. A stormwater quality management plan was completed to determine the locations of the best management practices BMPs needed, such as the underground detention basin and the proposed culvert.
The purpose of the water study is to calculate the demand of the facility and to recommend a size for the water pipes. To calculate the demand, the amount of fixtures were estimated, with With this estimation, a number of water supply fixture units was calculated using this table from the California Plumbing Code. Once the water supply fixture units were calculated, demand is derived from this graph in gallons per minute. The pipe diameter was calculated using these equations shown. Head loss, temperature, and roughness were assumed. We found that a 6-inch diameter pipe would be sufficient enough to meet the demand. This graph was used to find fire flow demand based on the type of building as well as area. With the previous information, we decided to implement additional fire hydrants in this layout shown.
For the sewer study, our purpose was to calculate the sewer demand for the Sharp MLB. What is considered for the sewer was the drainage water and the wastewater. It mostly consists of gray water and black water, which means that the water from the sinks, tubs, dishwasher, toilets that have human waste and toilet paper. In order to calculate the demand necessary required by the Sharp MLB, the water fixture units were counted. Each different fixture has a different flow requirement. By following the California Plumbing Code, we were able to calculate the total fixture units. With the total fixture units, we followed on the x-axis in the graph provided by the Plumbing Code and got to line number 1, and we were able to estimate approximately 88 gallons per minute. In calculating the flow demand based off of the fixture units, we also calculated the demand of gallons per person per day by using the water system's manual chart. Since hospital used from 150 to 250 gallons per person per day, we will assume around 150 gallons per person per day used. We anticipate an average of 350 people, 800 max. So for our following average flow, we ended up with 97 gallons per minute. But at a maximum capacity, we expect 236 gallons per minute. In order to know which pipe diameter met our demand, we used Manning's equation to see which pipe diameter allowed the sufficient gallons per minute to meet all our possible flow demands based off of the manual for VCP. Our final result ended up showing that a 6-inch pipe was the ideal size.
The purpose of the structure report is to provide the client, Sharp Healthcare, with recommendations for the construction of the structural shell of their medical office building. Analysis for the building shell, which will be constructed out of reinforced concrete, were calculated using standards and codes set up by both the City of Santee and the State of California. Codes provided by the American Concrete Institute, California Building Code, and the American Society of Civil Engineers were used for the preparation of the structural report. Project information. The proposed medical building will be composed of 3 floors at a maximum height of 40 feet. The total square footage of the 3 floors combined adds up to 83,000 square feet to comfortably accommodate visitors and staff. The first floor will consist of an L-shaped structure as to allow larger square footage, around 28,000 square feet, to accommodate for deliveries and drop-offs, while the second and the third floor will have a simple rectangular structure with 27,000 square feet each. Here we have the layouts for all 3 floors. Recommendations for the sizes of the slabs and columns are as follows. First floor, 8-inch PT slabs and 20 by 20-inch columns. Second and third floor, 8-inch PT slabs and 16 by 16-inch columns.
Based on the conditions encountered in the borings, the soil will not liquefy, so the building can be supported on footing bearings in a combination of tested and approved native soil and new fill. Subgrade improvement procedures are recommended beneath pavement to help provide more uniform pavement support. The proposed building can be supported on a shallow pouring bearing in the native silty sand or tested and approved new engineering fill. A combination of observation and testing by the geotechnical engineer will be required during footing construction to verify suitable bearing materials are encountered. Based on the results of the borings and anticipated grade changes, pavement subgrade could consist of native silty sand, soils, or new engineering fill. To improve subgrade support, we recommend that the upper 8 inches of the pavement subgrade be treated with fly ash. We recommend that a minimum of 13 to 15% Class C fly ash based on the material's compacted dry unit weight be used to treat the subgrade soils. The actual amount of fly ash should be determined in the field during construction as the amount required to stabilize the subgrade and reduce the material's plasticity index to value of 18 or less. Fly ash treatment should be performed according to Caltrans specifications.
Thank you for listening and giving us a hands-on experience of the industry, and especially pushing us for Design Day. We were given the ITE award and invited to a luncheon based off of our traffic study. We hope to see you guys again out in the industry. This is the end of our presentation.
Thank
Thank
you.
you.